My name is Antoine Browaeys, so I work at the Institut Optique as a CNRS staff member, so this is the French research organization, and we have a lab at the Institut Optique where we experiment with individual atoms, so we create arrays of atoms for quantum simulations. I'm also a scientific advisor of Pascal, who is also one of the partners of the project. And I was a co-founder of this company as well, but my role is just as a scientific advisor in the company. And I'm going to step back in history slightly. So when Pasquance 1 started, essentially we didn't really know the potential of this platform. It was essentially doing proof of principle experiments, and what happened during Pasquance 1 was precisely the demonstration of this is a very fruitful, efficient platform for quantum simulation. So that kind of established, if you wish, as other groups did as well at the same time, the potential of the platform. So within Pasquance 2, the idea is essentially twofold. The first one is we want to keep pushing the performances of the platform. So it means handling more atoms, having better fidelities, increasing the programmability of the platform. And so the idea here is that by enhancing the capabilities of the platform, you can tackle problems that are more subtle and more relevant to real condensed matter physics problem or real many-body physics problems. So this is the first challenge that we look at from the experimentalist point of view. The second challenge is when you operate relevant quantum simulations of a spin model or whatever, we want to assess how good we do that. In a sense, we want to, some people would talk about quantum advantage, although we don't really like this, this wording, but this is a wording that exists. The idea here is to know whether the machine performs well enough that indeed there is no classical way to simulate it. Because we always have to remember that it's not because we operate with hundreds of atoms that necessarily the machine has a potential quantum speaking, in the sense that if the machine is too noisy, then what you obtain is something you can usually simulate classically. So here the whole point, and this is done in collaboration with the theorists from the consortium and other experimentalists implementing their methods or expanding their method, is trying to assess how much noise we have to calibrate it and whether we can characterize the correlations, the quantumness of the system, if you wish. So this is really a daunting task, but that's one task that we are looking once again at the experimentalist. The industry partners within Pasquance 2 covers a wide range of competencies. So you've got people developing new lasers, developing cavities, developing optical modules. You've got people developing softwares. You've got people developing a full hardware, as Pascal, AQT, Planck actually do. And so their role is absolutely critical. You also have people developing high-performance computing. So for example, Eviden is one company that does that. And which is very important to be able to run large-scale classical simulation to benchmark against what we obtain in the lab, for example. So the thing which is very important in terms of having them in the consortium is the fact that we can have extremely efficient and rapid exchange between them and us in the academic world. So if you want, for example, to develop a high-power, low-noise laser, they have the capabilities to do that. They can generate a prototype by talking to us through the framework of Pasquance, and then they send us, or they build these machines, or this laser, we test it in the lab, we see what works, what doesn't work, and then we feedback on them. So this is a very efficient way of developing the technology that enables quantum simulators to be pushed forward and develop even further. So this is a very important role that they are playing within the consortium. This is a very tough question, and we wish we all had the answer to that, and especially the companies like Planck, Pascal, AQT wish they had the answer, because, I mean, of course, for them it's going to be a market. They're going to sell a product at some point. There are, of course, all these grand promises of being able to design better material based on intimate knowledge and understanding of their quantum properties, that you could do quantum chemistry. Okay. it's fair to say we are still far from this kind of applications. You also hear sometimes that those machines could operate the same kind of simulation that we do classically, but now at a much less energy cost. Our lower hanging fruits are optimization problems. But here we have to be very careful because there is a debate about really whether optimization problem can lead to an advantage with respect to the classical solution that exists. Nevertheless, you may not exclude, and this is still an open question, an open line of research, that there is some kind of niche problem where indeed we will be able to find more efficient algorithm. And for the people in the industry, this is critical because even if you don't wildly change, let's say, the class of complexity of the problem, changing sometimes just the prefactor in front of an exponential can be for them a huge financial gain or a huge time saving in terms of, the realization of a process. So this is the kind of thing that we are looking for at the moment, and most likely this is where we can expect some interesting results for the industry in the short term. All the other promises, we need to develop the platform further. And so it brings me to a kind of very important point, which is we still need the academia to have a very strong role here. I mean, we cannot decide that now most of the basic science has been done and we should just give it to the companies and the startups because this is mature enough. This is not the case. Some aspects are mature, some are not, and discoveries and surprises will still occur in the academic. So this is very important that the policy makers and the decision makers and the people from the industry understand that this is going to be a long-term process and we still need support for that. When I started this manipulation of individual atoms, that was about 20 years ago now, when I was hired at CNRS, and at the time my only interest was just, how much can we push the control that we have on the simplest quantum system you can imagine, in a sense, which is an atom. At the time, I had no vision about, many body problems. I was kind of clueless about that. I learned about that as the field emerged. So I wouldn't claim that I had a vision about this. And then we did some kind of important experiment that demonstrated that indeed you can entangle the atoms using a controlled interaction and all this. Of course, the interest in moving towards many-body physics was also triggered by the discussion I had with many colleagues from various sides, so it's just meeting the right people at the right moment. And in a sense, the creation of Pascal, that I'm also a co-founder of, emerged from discussion we had with people. That's not something that was also particularly visionary, but for me it was very interesting because at some point I was also interested in seeing how much the quantum could be used for applications. Sometimes the kind of problems that we look at in the academia look a bit exotic. They are very hard to convey to the real, to the layman of the people in the street. And so it's interesting to see how much it could have an impact in their life. So in our group, we keep doing and exploring fundamental basic problems, in particular in collaboration with, of course, all the people from Pascal. So it means trying to improve the experimental technique to manipulate the atoms, implement certain models that our theory colleague gives us. And the reason for that is because as I have this other activity of scientific advisor, I have the feeling that the application, my interest in application is already covered through the advising at Pascal. So in the group we really, and it's explore basic science, and it's also because we're doing that with PhD students who are interested in this kind of basic problems. The kind of resources we have are just more targeted towards doing basic science, and it because also I like it. It's also fair to say that the progress of those platforms are actually spectacular. Since the beginning of Pascal, I don't think anyone would have anticipated to see manipulation of so many atoms, so good control, and the exploration of so many of those models. So this is a very exciting time.